So my talk is going to be on a few topics. First, I'm going to actually be discussing the story of duality, which is actually not necessarily related to the more specific topic of deconfined quantum criticality, which I'll talk about at the end. And so this is based on a few papers, paper just by me a couple years ago, then one with these condensed matter people, and then one with Ning from last year. Okay, so what is this concept of IR duality? So IR duality is when you have two quantum field theories that are different at small scales, what we call the UV, but they become the same conformal field theory at large scales, what we call the IR. So usually in this scenario, one of the CFTs is weakly coupled in the regime where the other is strongly coupled, or they are both strongly coupled. So another way of saying it is that classically, each theory looks very different, but as a result of quantum effects, they in fact become identical, which is why this is an interesting and surprising phenomenon. Since usually at least one such theory is strongly coupled, it's very hard to check these IR dualities. And so when the space-time dimension is bigger than 2, usually you require supersymmetry to check. And so kind of the original versions of these dualities were various supersymmetric theories in 4 dimensions or 3 dimensions. But of course, this is a condensed matter conference, and so we don't like supersymmetry. And so instead, we want to study theories that can actually appear in nature. And so for dualities that can apply to systems in the lab, the first experimentally relevant system was actually proposed many years ago in the 70s by Peskin and then Dasgupta and Halperin. And this is called particle-vertex duality. And so in the modern language, this duality says that if you have quantum electrodynamics in 2 + 1 dimensions with one complex scalar, what's called the Abelian-Higgs model, then this is supposed to be dual in the IR to the critical O2 Wilson-Fisher fixed point. And so the application experimentally is that this describes continuous phase transitions between a superfluid and mod phase of the Bose-Hubbard model and integer filling on a 2D lattice. So how is this duality checked? Because it's very strongly coupled. And so the way it was checked is that you could do lattice simulations of Hamiltonians describing the theories on each side of the duality independently. So for the O2 Wilson-Fisher fixed point, this has been studied, for many, many years using lattice. More challenging is to do it for QED3 with one complex scalar. This was also accomplished in these various papers over the last few decades. And so you get the following check. So here is a list of critical exponents, or what I would call them scaling dimensions, as computed using the lattice model for each of these supposedly dual systems. So this would be the singlet, and then these would be various charged operators. And as you see, you get fairly similar numbers using each simulation, and this gives you the evidence that these two theories are likely to be dual. Of course, this isn't a proof, because these are just numbers, but, it's fairly compelling, I would say. Yeah.
So I think for this QED3 theory, you have Chern-Simons term?
No. No. So for particle vertex duality, there's no Chern-Simons term. We'll talk about Chern-Simons term later. No. So there's no Chern-Simons term here. Yeah. Okay. So that was the original duality, which is particle vertex duality. A more recent version of duality, which indeed does involve Chern-Simons coupling, relates theories that actually involve fermionic degrees of freedom to ones that have bosonic degrees of freedom. So this was done more recently by some of the authors who are in the room. And so one such example of this duality is, again, QED3, now with one complex 2-component fermion and Chern-Simons level at -1/2. And this is supposedly dual, again, to the O2 Wilson-Fisher fixed point. So different duality, although one side of the duality is the same. And so people call this duality 3D bosonization in analogy to 2D bosonization, although, of course, they're very different. Because 2D bosonization is some kind of exact mapping. It's basically like a rewriting of the variables. And so, maybe this is a matter of taste, but I would say it's somehow more trivial because it's something which is just exact along the entire RG flow. This is in contrast to 3D bosonization, where it is just an IR duality. So it is something which is false classically, but only becomes true in the deep IR due to quantum mechanics. So it's a bit more surprising. So another such duality was also recently proposed, which relates to theories both with fermionic degrees of freedom. So now you have QED3 with one complex fermion and 0 Chern-Simons level, supposedly dual to one free complex fermion. So these are all very fascinating dualities, but they're extremely challenging to check. Because usually the way you would check these dualities, you would have some kind of like lattice simulation for either side of the duality, as we saw for particle vertex. But because these dualities involve Chern-Simons as well as, fermions, it's much more challenging to do the lattice simulation, to do the sign problem, and various similar issues. And so this is why so far it's actually been very challenging to get evidence for these dualities. Another interesting aspect of these dualities is what's called the web of dualities story. And so there's a claim by these authors from a few years ago that these various dualities were all kind of related. And so the way you can derive one duality from the other duality, not derive rigorously, but I would say give evidence, is using something called these S moves and T moves. So the S move is that you take the Lagrangian on either side of the duality and you gauge a global symmetry. The T move is you take the Lagrangians on either side and you shift the Chern-Simons level by 1. And so with these two moves, you can derive all the dualities starting from a seed duality. So for instance, let's consider this seed duality, which would be QD3 with one complex scalar and Chern-Simons level 1, supposedly dual to one free complex fermion. So in the language of this S and T, let's say fermion means free fermion, scalar means, free scalar, and then we act with T, which makes the Chern-Simons level 1, and then we act with S, which gauges it. And so this is why the thing on the left-hand side is what I call QD3 with one complex scalar, Chern-Simons level 1, in this notation. And so then, to derive another duality, I act with S inverse and T inverse, so then I get scalar, by which I mean Wilson-Fisher fixed point of a scalar. And this is supposedly dual then to a fermion, which you have now gauged and shifted the Chern-Simons level, which is indeed one of the other dualities we discussed before. And so this kind of shows an example of how from one duality you can get another duality using these S and T moves. Although I want to emphasize this is not a rigorous derivation, because you're applying this S and T to the UV Lagrangian, whereas the dualities are supposed to be true in the IR. And so I would say these are more suggestions than they are derivations. So another way you can try to get evidence for this web of dualities is you can show that the Tufts anomalies match between each side of the duality. But like the best evidence would be to actually compute scaling dimensions, i.e. critical exponents using a lattice simulation and compare them. And that has not been done, unlike particle vertex duality. So that's why I would say, even though these dualities are very interesting, I would say the evidence is probably still fairly weak at this point. So what are ways people try to motivate the seed duality? The seed duality being this one, QED3 with one complex scalar, Chern-Simons level 1, dual to free complex fermion. So different ways you could try to motivate it. First of all, you could try to look at a more general class of theories, which has NC colors, QCD3, and then in the large color limit, you can actually do calculations. It becomes weakly coupled, and then you can check this large color version of the duality. You could compute various quantities, check that they are the same, and then you could try to boldly extrapolate to one color. But that extrapolation in practice isn't a very good one. I mean, like the scaling dimensions you get would give kind of crazy numbers. Another way you could try to motivate it is that you could start with a supersymmetric version of the duality, and then you could try to flow to a non-supersymmetric version. But this flow is uncontrolled. Finally, you could consider two lattice descriptions of the theories, and then you could show on the lattices are exactly related. But again, the whole point of the duality is a statement about the IRCFT. And so just showing that the UV description is related, doesn't necessarily say too much about the IR. Okay, so in this talk, we're going to try to check these dualities by computing monopole operator scaling dimensions in a large flavor and Chern-Simons level expansion for QED3. And then we're going to check two kinds of dualities. First, we're going to extrapolate to one flavor in Chern-Simons level 1 to check this boson-ization duality. We're also going to set Chern-Simons level 0 to check particle vertex duality. So in particular, we're going to define monopole operators. I'm going to go incredibly quickly through the calculation because I have limited time. I'll just show you the results. You can always look at the slides later. And then at the very end, I'm going to talk about deconfined quantum criticality, more relevant to what Yinchen was talking about, and this bootstrap evidence that it might be tricritical. Okay, so first of all, what is the Lagrangian we use to define our model? So this is what's called the CPN model plus a Chern-Simons term. So we have like a gauge theory for U1 gauge symmetry. It has a phi to the 4 coupling, which you can write using Hubbard-Stratanovich field. And then there's two complex scalars phi, as well as the Chern-Simons term. In the IR, it turns out you can actually set the first two terms to 0 because these are irrelevant operators in the UV. And so we were shown many years ago that in a large flavor limit, this flows to an interacting CFT in the IR. Although, of course, the big question is, does it continue to flow to an IR CFT even for small values of n? That is hard to say because, of course, it's strongly coupled. And so there's two kinds of operators you can construct. One type of operator you construct using the operators that show up in the Lagrangian. So you have your complex scalars phi, you have your Hubbard-Stratanovich field sigma, you have your gauge field, and you can use those to combine gauge invariant operators. And then you can study their scaling dimensions by doing Feynman diagrams in a large n expansion, as shown in ancient times by these authors. Now, the operator which I'm more interested in, though, are monopole operators. These operators are defined to be charged under this other global symmetry. This is called the U1 global symmetry. It exists for gauge theories in 2+1 dimensions, basically due to the Bianchi identity, because this field strength is conserved. And so these operators are not formed out of operators that show up in the Hamiltonian or the Lagrangian. Instead, they're defined a bit more abstractly as being charged under this kind of abstract U1 symmetry. Their charge is quantized. We choose to quantize it with half integers. And And when turn time is level is 0, these monopole operators are scalars under the global symmetry, as well as singlets. And when turn time is level is non-zero, though, you have to kind of dress the operators such that they start having non-trivial representations. And so the basic way of studying these operators, you compute them in a large flavor expansion. This was actually first done by Subir and Murthy back in 1990. A more efficient method was later shown 12 years later by Kapustin and collaborators. So we're going to use the latter method. So in particular, the idea is, again, the state operator correspondence, as Yidshin spoke about, which is that for a CFT, you can map energies on the cylinder S2 cross R to scaling dimensions in flat space, which is what we care about. And so the way Chern-Simons term enters is that it contributes a certain magnetic flux to the Gauss law constraint. And so this means that if you're trying to compute the vacuum in the presence of this monopole flux, which is what you want to do to compute the monopole operator scaling dimension, now if you have a Chern-Simons term, your vacuum is no longer gauge invariant. And so that's why you have to dress with extra fields, and this is why monopoles in the presence of Chern-Simons coupling no longer are singlets. They now will transform just like these fields. So in practice, what we do is we compute the thermal free energy on S2 cross S1. So we kind of regularize R to become a circle. We eventually take the circle to go to infinity. And then we just compute this free energy using a saddle point approximation at large n. And we are going to do this to subleading order. So I'm going to skip over these details due to limited time. Basically, I can just tell you that the leading order answer looks basically like a Casimir energy on S2 cross R. So this is the leading order energy. You're summing energies of basically your operator on S2 cross R times their degeneracy, plus you have an extra term corresponding to the extra fields you dress with in the presence of non-zero Chern-Simons coupling. You also have entropy, which you can read off from the thermal free energy. And this we end up interpreting from the fact that, at least at the large flavor limit, there are many operators which have the same degenerate scaling dimension. Now, this is only, of course, in the strict large flavor limit. Of course, at finite flavors, these would have different scaling dimensions. This is only kind of in this, rather formal large n limit. So this is the leading order answer. We also did it to subleading order, which is a much more challenging calculation. It involves basically computing fluctuations to the saddle point, but we did it. So let's just kind of skip ahead to the results and how they are relevant to these dualities. So let's first discuss particle vertex duality, which is the case. So we take our answer, which is in the large flavor limit when n is very large, and we're going to very boldly extrapolate this to one flavor. Now, this might seem like a crazy extrapolation. Why should this give anything reasonable? Well, just wait and see, and the evidence will speak for itself. So in this duality, one is trying to compare a monopole of charge Q in the scalar QED3 side to the lowest dimension operator made out of two Q complex bosons in the Wilson-Fisher side. So to give an example, this lowest charge monopole should be dual to a single scalar in the Wilson-Fisher. The second lowest charge monopole is like two scalars. Third lowest charge is like three scalars, etc. Very simple correspondence. All these operators are unique scalars, which makes things life a little simpler. And what's nice is that on the Wilson-Fisher side, there are very accurate estimates for the scaling dimensions of these operators as computed from numerical bootstrap. And there's an even wider class of operators which have been computed using lattice simulations. And I guess Fuzzy Sphere is also working on this problem. So, there's many different methods to compute scaling dimensions for the Wilson-Fisher side. That's kind of the more trivial side. The non-trivial side is the QED3 side. That is the side for which there isn't really such a good, well, I guess in this case there is a lot of simulation, but in any event, we're going to be using this large flavor expansion. Okay, so now here we show the results, and we show the magic. So in this table, we're looking at many different monopole operators, going from Q equals half all the way down to Q equals 5, and we can look at even more. But let's just look at these 11, for instance. So this was the leading order answer from the large flavor expansion of the scaling dimension. This is the subleading term, which was also computed. This was computed in a paper by Subir and collaborators. And so this leading term scales like n, and the subleading term goes like n to the 0. And so we want to extrapolate it boldly down to n equals 1, which means that we simply add these two numbers together to get this number. And then we want to compare this to the scaling dimension of the operator that's supposed to be dual on the Wilson-Fisher side. And so lo and behold, upon making this comparison, you see that all these operators match to like shockingly good accuracy. So, a priori you would say there's no reason why extrapolating n infinity to n equals 1 should give anything reasonable. And yet, for every single operator we looked at, they actually match pretty good. I mean, look, 10.6, 11, 9.1, 9.7, etc. So I think this is rather magical. Because, for instance, if you were trying to compare other operators in QED3, non-monopole operators, those have also been computed in a large flavor expansion, and that expansion is terrible. So if you take that expansion and if you plug in n equals 1, you get like negative numbers. You know, like it doesn't make any sense. And so there seems to be something very special about the calculation of monopole operators, which seems very robust, even for a very small number of flavors. And in fact, I mean, even the scaling of the calculation is different, because monopole operators, they scale with the number of flavors n, whereas non-monopole operators scale again to the 0. So this is the first rather surprising result, that this large flavor expansion seems to work very well, even for one flavor, as checked against this particle vertex duality. In fact, in Subir's original paper, they actually compared their answers for this large flavor expansion, not just to the n equals 1 case, which is particle vertex, but to larger values of n, for which other lattice simulations have been done. And lo and behold, it seems like their large flavor expansion answer actually matched pretty well for all the values of n that they looked at. So in this plot, the x-axis is 1 over n. The y-axis is their answer for the scaling dimension normalized by n. And so because they computed it to subleading order, their prediction is just a line. And then these things are various lattice simulations done over the years, and as you see, they actually match pretty well. Okay, so that was the first duality we were going to discuss, which was particle vertex duality.
So can you check the tricritical point of the ultra mono and tricritical point of the scalar QED? Because like the tricritical point of the ultra mono is free theory.
Yeah. So okay. So indeed, one could try to make the comparison. That would be a good comparison to make. No one has yet computed monopole operator scaling dimensions for the tricritical QED3. So the calculation would be slightly different, because in your Lagrangian you would have basically one fewer term. I mean, you would no longer have this Hubbard-Stojanovic term, and so this would just give a different answer. And so no one has done that calculation. It would be a very interesting calculation to do, because indeed, there are some proposed dualities that it should then be dual to just a free scalar. Yeah, so I do think that would be something nice to do. Well, these calculations are very challenging, so I encourage more people to work on this, because, then maybe we'll have more results sooner. But yeah, but indeed, that would be something very nice to try. Okay. So, yeah.
Isn't it really kind of matching because the order n term is about vector of
yeah. It is quite magical, yeah. So that is what's so surprising about this. I mean, if this would have worked for one or two things, I would have said, who cares? This is clearly a coincidence. But it's the fact that this works for 11 different numbers, which makes me think that something must be going on here. And we could check even more numbers in principle, and they all work. So when you have infinite coincidences, then it's not a coincidence. Yeah. You're saying on the Wilson-Fisher side?
Yeah.
Oh.
As I recall, they're basically pretty well fit by quadratic function.
It's not quadratic, it's q to the 3 halves. So there's this large charge expansion, which says that when you look at operators with a sufficiently large charge, they start scaling like q to the 3 halves. Yeah, so indeed, you could argue that maybe once you've checked a few, the fact that the other ones also work is maybe because for sufficiently large q, they're just following some general curve, which is fixed by a few parameters. Yeah, so indeed, that's a good point. But I actually checked this just to see if this was just a coincidence. It is very sensitive, though, to because you have to fix a few numbers to then get that scaling. And so if you would have fixed those few numbers slightly different, you would have gotten kind of crap results for everything else. But I agree that you could say that maybe this coincidence is more of a coincidence of maybe 3 or 4 numbers rather than a coincidence of infinite numbers. Yeah, so that's a good point. Anyways, okay, so now let's talk about this other duality, the more interesting one, because the previous duality particle vertex, there was already evidence because you could just do lattice simulations on both sides. So that was more of a test case, rather than a truly new result. The more new and interesting result is this 3D bosonization, in particular the seed duality, which implies the other dualities, which is that scalar QED3 with one complex scalar, insurance times level 1, is dual to free complex 2-component fermionic theory with fermion psi. So one aspect of this duality which is kind of interesting is that the free fermion theory is parity invariant, whereas scalar QED3 is, at least from the Lagrangian perspective, would not seem to be parity invariant because it's a Chern-Simons term. So in order for this duality to make sense, you basically have to conjecture that the k equals 1 theory is related to the k equals minus 1 theory, which is one of the things these people did in their original paper. So in this duality, the idea is that the monopole of charge q should be dual to the lowest dimension operator made out of 2 q fermions, where you will have half integer spin when q is half integer. So for instance, the lowest charge monopole is dual to a single free fermion psi, which has spin half. The second lowest charge monopole, M1, is dual to this composite of two fermions, which now has spin 0. So even though this is a free fermion theory, it's not totally trivial, because as Q gets bigger, you have to start dressing your fermions with derivatives, because otherwise the operator would just be 0, because the fermion is all anti-commute. And so to give kind of the lowest non-trivial example, say we're trying to relate the charge 2 monopole to the 4 fermion operator. So we have 4 of these fermions. We have to dress with 2 derivatives to get something non-zero. And there's 2 different ways of contracting the indices of these derivatives. So that means there are 2 degenerate operators in the free fermion theory. They both have dimension 6, but one has spin 2 and one has spin 0. And this is kind of a generic phenomenon. As Q gets bigger, there's going to be many degenerate operators in this free fermion theory. And this is actually going to end up being kind of relevant, so it's something to keep in mind. So how do we count the operators in the free fermion theory, taking into account these degeneracies? It's not totally trivial. So one way of doing it is you can compute the spectrum of a free fermion theory by looking at the free energy on S2 cross R in the presence of some background flux for the U1 global symmetry. And so then you have fermionic modes of various half-integer spins J. They have various eigenvalues, and then you just kind of like fill up, your energy shells with these eigenvalues, and this will tell you what the appropriate operators are. I mean, it's a free theory, but it's not a totally trivial free theory. And so one kind of curious fact you learn from this energy shell perspective is that operators with charge Q that correspond to states of n filled energy shells are unique scalars. And this only happens for special values of Q, because this is where you're filling up the energy shells. So this happens for Q equals 1, 3, 6, 10, etc., according to this pattern. And for these special values of Q, the scaling dimension, you can write in closed form, it's, 2/3 Q square root of 1 plus 8Q. So for instance, I mentioned this Q to the 3/2 scaling. Well, you can clearly see when Q is large, this goes like Q to the 3/2. But of course, because it's a free theory, you just have the exact answer. And so here are some examples of the scaling dimension you get. For other values of Q, which do not fill up these energy shells, these operators will be either non-zero spin, or they will be degenerate. And so as we're going to see, there's going to be kind of a difference between the operators that fill up the energy shells and the operators that don't. Okay, so now let's go ahead and compare the operators in the free fermion theory to the calculation of the supposedly dual operators from this large flavor expansion for monopole operators. So again, in this table, we look at many different operators. Here we kind of skip ahead in Q, so we all go up to Q equals 21. The first column is the leading large n term. Second column is the second large n term. We extrapolate n equals 1, so we just add the two together, and then we compare it to the operator that it's supposedly dual to. So let's focus on these purple values, and let's ignore the black values to begin with. So for Q equals 1, the prediction is 2. We find 1.95. That's a relative error of 2.4. Now let's look at the next purple value. So again, these are the operators in the free fermion theory that are filled energy levels. So next operator is Q equals 3. Prediction from free fermion is 10. We say 9.859. Relative error 1.4. So as you see, the relative error is getting smaller and smaller. So once we get up to Q equals 21, our prediction was 180.5, and the free fermion is 182, which is a relative error of less than 1%. So this is an insanely precise matching. I mean, I don't know of an example in theoretical physics of a perturbative expansion to 2 orders that matches to less than 1% relative error. I mean, like, it's crazy how well this thing is working. And this works even better than the particle vertex case. In the particle vertex case, the relative errors was something like 5 or 6%. And in that case, the relative error wasn't going down. Here, the relative error seems to be maybe even going to 0. So it might even be the case that as Q goes to infinity, literally you get exactly the right answer. So an obvious question, though, is, well, why am I talking about these purple values? What about these black values? The black values don't seem as good. For instance, with Q equals half, the large flavor expansion says 0.72, whereas the answer is supposed to be 1. So there seems to be something special about these purple values, which are the operators, which are the unique scalars, in contrast to the black values, which are either non-scalars or degenerate. So let's talk about those other values of Q for a moment. So operators in the free fermion theory that are not unique scalars don't seem to match our monopole calculation, as we just discussed. Even though I will say the discrepancy is getting smaller, but still, the discrepancy is huge. I mean, it's 28% versus 2.4. So one thing that might explain this is that after all, the large flavor expansion that we used assumed a certain saddle point that we expanded around. Perhaps that saddle point only makes sense for monopoles that are unique scalars, and maybe if your monopole is spinning, you just need a different saddle point, and so maybe our calculation is just invalid, for such operators. So that's one possibility. But there's something kind of intriguing that we observed, which is that let's take the answer on the free fermion side for the unique scalar operators. So remember we had this exact answer. for these field energy shells. And this is only supposed to apply to special values of Q. You know, Q equals 1, 3, 6, 10, etc. But let's just decide to analytically continue this formula to the other values of Q where it's not supposed to hold. And so when you do that, lo and behold, you actually start matching our prediction. So, you know, in particular, the large flavor expansion, we said 0.72. This formula with Q equals half gives 0.74. Similarly, for these other black values, you again find this match. And so this is suggesting something very curious. This is suggesting that the large flavor calculation of monopole operators is somehow capturing the large charge effective theory. So there's this whole story of large charge effective theories, which maybe some people in the audience are familiar with, which was first shown by Simeon Hellerman a few years ago, and now there's been many works involving condensed matter physicists in the last few years. And basically the idea is that when you have some CFT with a global symmetry with charge Q, when Q is very big, you could describe operators in that sector by some effective theory, which oftentimes is like some kind of like, I mean, there's various kind of descriptions of the effective theory. In the free fermion case, I think it's supposed to be a free Fermi liquid, which is actually kind of special. This was shown by this paper by Zora Komargatsky and others. And so this effective theory, strictly speaking, only applies to these special values of Q. But it might just be the case that for reasons I don't fully understand, this large monopole operator expansion is just capturing, you know, this effective theory, and this is why it gives the answers for every value of Q. They are only physical for the special values of Q, but for the other values of Q, they just anyways give the right answer. So, you know, that's a possibility. Okay, so in the remaining 5 minutes, let's discuss deconfined quantum criticality, in particular this neo-VBS phase transition that Yin-Shen was discussing. So this is just a review of this deconfined criticality story. Yin-Shen already discussed it, so I think we can kind of skip over this. And so, as Yin-Shen discussed, you know, people did a lattice simulation originally by Nahum et al., where they claimed to find SO5 symmetry enhancement from the original SU2 cross U1 symmetry. In particular, they gave evidence for this SO5 by showing that different operators would actually had roughly the same scaling dimension. And so one important aspect of the story is that if you assume that the theory was critical from the SU2 cross U1 perspective, i.e. there was one relevant singlet, and then if you assumed SO5 symmetry, that relevant singlet became part of the rank 2 of SO5, which is not a singlet. So that means if SU2 cross U1 is critical, that would mean that SO5 has no relevant singlet, which is a very kind of like bold conjecture, and that bold conjecture was cruelly destroyed by a bootstrap analysis, which you could do basically in 2 minutes, because you just do a bootstrap bound for O5 symmetry, assuming no relevant singlets, and you see that everything is ruled out. And so this is what led to the confusion, which Yin-Shen discussed, that perhaps the theory is a non-unitary CFT, which Yin-Shen shows some possible evidence for. Instead, though, here in my last couple minutes, I'm going to try to show some evidence for an alternative possibility, which is that it's tricritical, which I understand might not be the right terminology. Basically, I'm just saying that there are 2 relevant singlets from the SU2 cross 1 perspective, and thus 1 relevant singlet from the SO5 perspective. So that is the scenario I want to show evidence for. Note that I'm doing bootstrap, so I'm only talking about a CFT. So I'm not talking about a phase diagram, I'm only talking about a CFT. So what do I do? So what I'm doing is that I'm bootstrapping correlators of SO5, and I'm looking at 4-point functions involving a singlet, a vector of SO5, and a rank 2 of SO5, S, V, and T. And so I look at the system such that I will have access to as many operators as possible. In particular, I will have access to these operators as well as the rank 3 and the rank 4, because those will show up in the OPE of these operators. So what I do is that I assume run 1 relevant singlet under SO5, which again implies 2 relevant singlets under SU2 cross U1, as well as 1 relevant vector, 1 relevant rank 2, 1 relevant rank 3. This is motivated by large N, as I'll say in a moment. So this is a fairly large system to bootstrap. You know, for the experts, there's 29 crossing equations. So this, in order to bootstrap the system, you have to use the most cutting-edge bootstrap technology, which is called skydiving code, which was only developed in the last year. So this wasn't even possible until a year ago. And the reason why it's so challenging is that there's just like a huge space of parameters that you're kind of bootstrapping around. And so the result of this bootstrap study, without knowing anything about bootstrap, is that you just get an allowed region in the space of these parameters. So think of some like huge dimensional space. Certain values of these parameters are allowed. Certain values of these parameters are not allowed. You know, so it's some like high dimensional space. So oftentimes in bootstrap studies, people observe that real physical CFTs show up on the boundary of these allowed regions. So this was shown originally for Owen Wilson Fisher fixed points. It was also shown in a paper I had about QED3 for fermions. Yes? With for fermions? Yeah. Well, I mean, okay, I understand there's some debate, but I say there's some evidence from my paper back in 2016 that.
The larger results.
Sorry?
The larger expansion results, if you extrapolate to.
Yeah. Yeah. Yes. Exactly. Yeah. Sure. Yeah. So there is some evidence that QED3 with 4 fermions might saturate the bound. Of course, this is not a fixed story. The story, which is somewhat more rigorous, is that the Owen-Wilson-Fisher fixed points definitely do saturate bootstrap bounds. Yeah, but I understand for QED3 with 4 fermions, there's still some debate about that. And so this kind of motivated us to look at some point on the boundary of the allowed region. How do we choose that point? Because we have some big region. Well, we chose it by fixing the value of the scaling dimension of the vector. Now, there's two ways you could motivate this value of 0.63. Either you could motivate it from the large monopole expansion, which I've been discussing this whole talk, and which I'll review in the next slide. Alternatively, that's also the value which was given by Nam et al.'s original lattice study. So depending on your taste, you could say it was either motivated by previous lattice studies or by this large flavor expansion. In any event, though, we fix this point on the boundary, we maximize delta t, and then we just read off all the CFT data corresponding to that point on the boundary. Because points on the boundaries of bootstrap bounds are approximate solutions to crossing, and so it means you can read off all the CFT data from that point. Okay, so this is what we do, and here are our results. So the top line is the result from our paper, which came out last year. So again, we put an asterisk here because this is the value we fixed. This is our input. And then these are the outputs. These are the predictions from our bootstrap. And so one thing which was kind of nice about what we observed, which kind of motivated us to write the paper in the first place, is that if you take the large flavor expansion of monopole operators, extrapolated down to n equals 2, which is the CP1 theory, so first of all, 0.63 is, what motivated us to look at this point, but the non-trivial thing is that it seems to, pretty closely match these other monopole operators. So it's like you could say we put in one value, and we find a pretty good match for 3 other values. Delta t, rank 2, rank 3, and rank 4. Of course, there was no large n prediction for the singlet, and so this 2.359 was just a completely original conjecture. So Yinshen in his talk discussed the fuzzy sphere. So this is just to show some kind of comparison that actually, curiously, the numbers are actually not that different. So even though Yinshen's interpretation was a bit different, that he's finding some pseudo-critical CFT, nonetheless, the actual numbers are not that far from what we observe. 1.45, 1.5, etc. I would say the biggest discrepancy is the value of the singlet, where Yinshen is showing a rather larger value, 2.8, whereas we're showing something like 2.3, 2.4. Most exciting, though, from our perspective, is this paper by Sandvik that came out last night, which seems to confirm our conjecture. Because in this lattice simulation, they find these numbers which are extremely close to our values, with relative errors of just 1 or 2% for every single one of these numbers. I added an additional line to this table, which I call Bootstrap 2024, simply because, as I've emphasized, the way we do our bootstrap study is we fix the value of delta v, and then we read off these other values. And delta v, we might be slightly off. And so, just to do a slightly better comparison and to kind of show you how these values are changing, we did the exact same bootstrap study, just putting in this different value of delta v, slightly smaller value. And as you see, our values kind of go down. So it seems like our values kind of change monotonically with the value of delta v. And so in particular, if we want to compare it to Sandvik's study, because his value of delta v was a bit smaller than the one we chose here, now we choose a slightly smaller value, and then our values get even closer. Although even the original values were already close within 1 or 2%. So, okay. So I will go slightly into my discussion time by concluding. So conclusion, we've computed monopole operator scaling dimensions in a large flavor insurance Simons level expansion with fixed ratio to subleading order. This is kind of the rigorous analytic calculation. This generalized previous results for zero Chern-Simons coupling. We showed that after extrapolating this large flavor expansion down to n equals 1, when k equals 0, this matched particle vertex duality, rather surprisingly. But even more surprisingly, when we extrapolated for Chern-Simons level 1, we were able to match infinite different operators in this putatively dual free fermion theory. And so I would say this is the first dynamical evidence for 3D bosonization, from a very surprising perspective. Now, so far, this check only seems to work for the infinite values of Q, which refer to unique scalar operators, but there is some intriguing connection to the large charge expansion for other values of Q. Finally, I also extrapolated this large flavor expansion to n equals 2, which is the CP1 theory, which is perhaps relevant to this SO5, the space transition. And in that case, we found that these large n values all seem to lie on a special point on the boundary of our bootstrap bound, which motivated us to conjecture that this theory was tricritical from the SU2 cross U1 perspective. All we mean by tricritical is 2 relevant singlets. So if you prefer bicritical, you can use that term as well. And in particular, our main conjecture was that the singlet is 2.36, and that seems to be roughly confirmed by Sandvik in his paper last night. So of course, there's many future directions. We'd like to better understand what's going on for these non-unique scalar monopoles. We'd like to maybe find an analytic proof of 3D bosonization in the large charge limit, because it seems like the error was going to 0, so maybe there's just a rigorous proof. There's also many other versions of this monopole calculation one could do. I mean, you could look at QCD3 theories, which have various tools. You could look at supersymmetric QED3. You could look at QED3 with fermions. All of these things are things I'm hoping people will be motivated to do based on these results. These calculations are hard, and I could like some help. Finally, it'd be nice to actually match an experiment to our prediction for the neo-VBS phase transition, which I guess maybe we'll hear about in this conference. And finally, there's kind of an somewhat analogous story of QED3 with two fermions. It's supposed to have enhanced O4 symmetry. This original claim that it was kind of critical from the SU2-SU1 perspective was ruled out by Bootstrap kind of analogously. But maybe here too, in fact, it's tricritical. And so maybe here too, one can actually show that this theory actually makes sense with enhanced symmetry, just that it's tricritical. Okay, that's it.
Great, thanks a lot. That was a great talk. And I can run the microphone to you if you don't want to get up. People have questions. Okay, so let's start with Max and then we'll go to Tyler.
Do you have the rest of the spectrum extraction? For instance, I don't know, antisymmetric, SO5 antisymmetric?
Yeah, I know people are interested in the antisymmetric one, as Slava mentioned. Yeah, I mean, we extracted the spectrum. It's not like super stable. I mean, because this is like a very hard thing to bootstrap. It took us a month even to run this one point. And so that's why we were trying to be conservative and only showing these kind of lowest few operators. But I mean, we have a spectrum. And so one could look at it, but I would not necessarily put my money, that all the other numbers will be super stable. They might change as, bootstrap precision goes up.
And if you go back to your bootstrap setup for the SO5?
Yeah.
Yeah, so delta T3 you also scan over?
No, I mean, delta T3 appears as an internal operator.
So I'm just looking at that.
Oh, sorry, you're right. Sorry, we did scan over it. Yeah, we did. Yeah, sorry. So to clarify, we look at 4-point functions of the rank 0, 1, and 2, and then that includes the rank 4 and the rank 3 internally. And the rank 3 is relevant, and so this is why we impose that it was relevant by saying there's only one operator below dimension 3, and then we scan over it. The rank 4 is not relevant, and so that's why we didn't scan over it. And so this is kind of summarized here. As you see, rank 3 relevant, rank 2 relevant, rank 1 relevant, singlet relevant, rank 4 not relevant.
Thank you.
Yeah, thanks. I just have a very simple, maybe, question about the technique.
Yeah.
So I was wondering why you need both large N and large K to control the theory. I haven't ever worked.
Well, I mean,
the
K is scaling with N, basically. So it's like, okay, first of all, in this application, K is 0. So here we're not doing Chern-Simons level at all. The point is that like you can make K non-zero. It's kind of a generalization, so you don't need it. It's just like when you're doing a large flavor calculation. Say you also want to be sensitive to the Chern-Simons coupling. If K did not scale with N at the order we work at, you just wouldn't be sensitive to it. And so that's why you get more interesting results by having K scale with N and then extrapolating them both down to 0.
So it's not like, so if you fix finite K and go to large N, the expansion is still controlled.
Yeah, it's still controlled. Yeah. The only thing you need for it to be controlled is large N. It's just that, like, if you want like a bonus and for it to also be sensitive to K, then you can have K scale with N. Although, for this application, K is 0. So like the only case where I used non-zero K was where I was doing 3D bosonization, which is an independent part of the talk.
I guess I'm just saying, I might have thought the naive thing to do is to fix some finite K rather than having K scale with N.
You could do that. It would make the calculation more trivial. So you kind of wouldn't be sensitive to K.
You would still be sensitive to K. It's just K is not scaling with N.
You would be sensitive to it at subleading orders in 1 over N, not at the leading orders in N we look at. Yeah. So of course there's some sensitivity, but just from the perspective of the large flavor expansion.
So if you do that calculation, you would not get the same matching? Or?
You would not get the same matching. Yeah, so it seems like, look, obviously this is non-rigorous because you're taking a large flavor expansion and doing an extrapolation. And so you could say like the mathematical statement is that there's some function of N and K and you want to do some analytic continuation from large N to small n. And it seems that for reasons we don't understand, the analytic continuation that works is the one where you start by scaling both of them to be big and then extrapolating them both down to 1.
I see. Thanks. That's very helpful. Yeah.
So this is a vague question and it's for both speakers. So it sounds like both of you are doing some monopole calculation on the sphere and find the finite size effect to be unreasonably small. Is there a guess why that's the case?
Well, I guess we're both involving monopoles, but I think in a very, very different context.
Yeah, of course.
Yeah, I think, yeah. I mean, the monopoles in this case is like literally the actual physical monopole operators. I think Yinshen can answer, but.
But when you do, when you do this, at the end of the day, you're calculating energy.
We are calculating energies on S2 cross R, yeah.
I mean, okay, maybe the more concrete version is there some guess of why the finite n or the finite monopole charge expansion will just work?
Well, I know that's the mystery. I mean, like, my conjecture is that it's related to the large, I suspect this is related to large charge effective field theory. And the reason why I think it's related is because the match gets better and better as the charge gets bigger. And this is why I even think that there might be a rigorous analytic proof of this 3D bosonization in the large charge limit, which I motivate people to try to look into. But like, this is just a conjecture. If I knew how to do it, I would have already done it.
Thanks.
But do you mean different CFT will have in the large Q expansion, different CFT will have same those three parameters, effective field theory?
Okay, so I mean, the large charge effective theory, it's not universal because it's like, so you have this expansion, it's like a number times q to the 3/2 plus a number times q to the half plus, some universal term. So those first two numbers are non-universal, and so that's why for different CFTs, even with the same global symmetry, you get different answers. The universality is just the scaling in Q. So it's the scaling in Q which is universal, but the coefficients are different. And so, the coefficients in a sense is kind of what we're reading off from here.
Yeah. And is there a non-abelian version for that?
There is a non-abelian version. Yeah, there are papers on the non-abelian version.
Yeah. So then I'm wondering whether the agreement between bootstrap, larger expansion, and also those lattice model simulations for the DQCP showed is similar to the story here that is actually just controlled by one or two free parameters, which happens to be very close.
It could be, yeah. That's always a possibility, because indeed you could say first of all, this is also assuming that the large charge effective theory is a good description for small charge, which is also something which is totally conjectural.
Right.
So in some sense you're just moving the onus of the magic from large N to large Q. But I mean, it happens to be the case that the large charge effective theory, at least in the simplest cases of O2 Wilson Fisher, does actually seem to work even down to the lowest values of Q, for unexplained reasons.
Okay.
Hey, nice talk.
Thanks.
I was wondering if your bootstrap analysis, there's some way to tell whether you're probing really a unitary CFT or you might be seeing this complex CFT in this pseudo-criticality scenario.
Okay, so it's a good question. So first of all, unitarity is an input to the bootstrap because the whole power of the bootstrap is you're assuming that these OP coefficients squared show up are positive, which is only the case for unitary theories. Now, you might say though, okay, but what if you're just very slightly breaking unitarity such that they're almost positive but slightly non-positive? And so the question is, how sensitive is the bootstrap to small violations of unitarity? So this is something which has been studied. So for instance, people did bootstrap studies in fractional dimensions for the Ising model, and there they got answers that matched the epsilon expansion, even though we know that in fractional dimensions, scaling dimensions are slightly complex. But in that case, we know from a paper by Slava-Richkov that the complexity is extremely small. It's like you have to look at operators that are dimension 20, and then they become very slightly complex. So in that case, it seems like the violation was so small you weren't sensitive to it. On the other hand, though, I would say the most relevant study is a paper I had with my collaborator Ning Su about the Potts model in fractional dimensions from last year. So there we looked at the three-state Potts model, and we were looking between dimensions 2 and 3, trying to find the critical dimension. And there we actually saw, by studying both the critical and tricritical theories separately, that they get closer and closer and closer until they merge and they both disappear. And so in that case, it seems that the bootstrap was sensitive to the violation of unitarity caused by merger and annihilation. And so I would say that if we were sensitive in the Potts case, enough that we don't get an answer once it violates unitarity, so too, if violations of unitarity were truly going on here, we would have also been sensitive. Although, of course, this is just my intuition. Might not be right.
Thanks. Are there unitary SO5 symmetric CFTs between dimensions 2 and 3 with no relevant symmetric scalar?
Not as far as I know, because that's a hard question to answer because they'd probably be strongly coupled. So there are various Lagranges you could write down that have SO5 symmetry, which perhaps...
But for same bootstrap analysis that you do in 3 dimensions to rule it out, you could do it between 2 and 3 and ask if it's that.
You could do that. I think Yinshin, didn't you have some paper with where you...
Some paper try to continue the SU2 level 1 version of written in 2D with the SO5 because following the proposal of Chong and then there we find that the kink of this T disappears at some fractional dimension, very similar to what Shai described for the Potts model. Yeah.
Thank you, everybody, for great discussion. Thank you, Shai, for a great
Thank you.
talk. And we will take a break and come back. So let's give Shai a applause.